Hello viewers, welcome back to our series of lectures on chemical bonding. In this concluding part of this series, we will take up the issue of covalency in ionic solids and talk about the energetics of dissolution process. The session is planned as follows, that is, to begin with, we will briefly review what we did in the previous sessions. Thereafter, we will bring in the concept of covalency in ionic compounds. We will try to argue out and establish that ionic compounds are not pure ionic compounds, they have certain element of covalency in them. And in this process, we will bring in Fajan's rules, which basically kind of puts forth or kind of summarizes the different factors which affect the covalency or which cause covalency in ionic compounds. Having done that, we will move on to the process of dissolution. We will try to discuss what is the process of dissolution. Thereafter, we will talk about the energetics involved in this process of dissolution. Having done this, we will come down to the dissolution of ionic solids. That is the main theme of today's session. And in this process also, we first see that what is the process of dissolution, how does it differ from the process of dissolution in general, and then also what is the energetics here, and then under what conditions we get good dissolution, or under what conditions we do not get the ionic compounds to be dissolved over there. And towards the end, we will try to sum up what we do in today's session. Now, with this brief outline, let us continue and start by reviewing what we did in the previous sessions. What basically we have done in the previous session was that we explained the formation of ionic compounds and introduced the concept of lattice energy in the process, because lattice energy is the energy released when 1 mole of a crystalline lattice is obtained from the corresponding ions in the gaseous phase. Having done that, we discussed the theoretical and experimental approaches to determination of lattice energy. That is, we talked theoretically how do we determine this, and then we also bring in the experimental approach to determination of lattice energy. Thereafter, we defined and explained intermolecular interactions. This was a very broad approach to all kind of interactions which are possible between different kind of species. It could be atoms, molecules, or ions and things like that. And we talked in terms of the interactions between polar, non-polar, polar and non-polar, and between ions and molecules. And in this process, we saw that what are these interactions and then how do they affect the behavior of the species involved in the process. This is what we did in the previous session. Now, let us go further and try to argue out that why do we say that the ionic compounds are not pure ionic compounds, they have got certain element of covalency there. Okay, let us recall this. In the ionic solids, typically we know that the ions are held together by strong electrostatic interactions. And further, these ions differ in the size and are assumed to be hard spheres. And at this point, hard spheres we have to take note of, because that is what we are going to attack in a short while from now. We also recall that when we talked in the previous sessions, we talked about a lattice energy, and then we theoretically formulated an expression to find out the lattice energy of an ionic solid, and we found that there is a reasonably good agreement vis-a-vis the theoretical prediction and the experimentally determined values of lattice energy for alkali metal halides. And the basic assumption here also was the hard sphere models. That means, since the agreement is reasonably good, we say that this hard sphere model seems to be appropriate for ionic solids like alkali metal halides and all. However, when we go on to similar data for silver halides based on the same hard sphere model, we find that there is enough of deviation there. We see that, say, silver chloride, bromide and iodide, we find this is the theoretical predictions here on the basis of hard sphere model, and what we experimentally observe are these numbers there. And then there is a deviation of about 6.8, 8.5 and about 12%, which is a significant deviation. That means the experimental determination, the data what we get from there does not match with the theoretical prediction. And the reason for that is that these deviations can be attributed to the covalency there, because we assume that our ionic solid, say silver chloride, happens to be a perfect ionic solid. That means there is ion, silver ion, there is a chloride ion there, and the two are interacting only as electrostatic charges there. But what we find from this deviation is that there is certain amount of covalency in them, and because of this covalency, this deviation is coming over there. Further, let us see that because we did talk about the structure of ionic solids based on the radius ratio rules, and these radius ratio rules, you will recall, are also based on the hard sphere models of ion. And what you find is that the predicted structures for different ionic solids here and the one which are experimentally observed, they differ, and this again kind of point towards the covalency in the ionic solids over there. That means this data of the discrepancies between the predicted structure types and observed structure types for different ionic solids also supports the kind of concept of covalency in ionic solids over there. Now, let us see what is the cost for covalency. We are saying that these two set of data, one of the lattice energy, one of the kind of ionic structures predicted and observed for the ionic solids there, they support covalency. But what is the reason for such a covalency to be there? The reason for this covalency is that this deviation can be attributed to two things there, because we have started with the assumption that ions happen to be hard spheres, number one. Number two, we assume that bond to be 100% ionic. These two assumptions are the foundations of our hard sphere model, and what we find now is that actual bonds are neither 100% ionic nor 100% covalent there. That is, the ions are not hard spheres but soft polarizable entities. That means that ions have got certain electron cloud which can be polarized there in such a way that the neighboring ions can affect each other. Because of these two things there, we find that certain element of covalency comes in. If it had been hard spheres, then it should have been 100% ionic structure, which it is not. Okay, let us go further a little and see that when we talk about the covalency in ionic compounds, we find that typically a positive ion will attract the electrons on the negative ion and repel the nucleus, thereby it polarizes the negative ion. What we see here is that we have got a positive ion here, a negative ion here. It was a sphere to begin with, but because of this positive charge over there, the electron cloud of this negative ion has got polarized. It has got kind of deviated from the original spherically symmetrical kind of distribution there. So, this small little polarization here is what is contributing to the covalency there. Similarly, what we find is the negative ion also. The negative also polarizes the positive ion, and what we find is that the extent of polarization done by the negative ion on the positive ion is much less as compared to that of the positive ion polarizing the negative ion there. It is so because in the negative ion, the electron cloud is much more diffused, it is easily polarizable, whereas the positive electron clouds, the electrons are held more firmly by the nucleus, it becomes difficult to polarize a positive ion there, but all said and done they do get polarized there. So, this polarization is what is responsible for some kind of an overlap between the ionic clouds or the electron clouds of the two ions there, and that leads to certain element of covalency, because you remember that a covalent bond basically means that some kind of an overlapping. So, this kind of polarization is the one which is responsible for the kind of element of covalency in ionic solids there. Let us move further. Further, what we see is that the larger negative ions are more polarizable than the smaller ones, which is obvious, because what we said was that we have a negative ion, the electron cloud is diffused there, easily polarizable by the positive ion there. But if this ion becomes larger, the electrons become even more diffused. So, what we see is that iodide ion, which is much larger in size as compared to bromide ion, which is larger than the chloride ion, which is larger than the fluoride ion. So, that is the order of the polarization, the extent of polarizability of different ions over there. So, larger negative ions are more polarizable than the smaller ones there. That is, as we said earlier, the electrons are farther away from the nucleus, easily polarizable there. When we talk about the polarization, because essentially when talking about the covalency, that depends on the polarization of the electron clouds of the ions there. And what are the factors on which this polarization depends? There are two main things there. The first one happens to be the polarizing power of the ions, because there is an ion which is trying to polarize the other one. So, how powerful is this ion which is going to polarize the other ion there? That is number one. The power of an ion to distort the other ion, that is called as the polarizing power of that particular ion there. Typically, what you find is that the polarizing power of an ion to distort the other ion depends on size of the ion. Smaller the ion, it is better, because smaller ion will be able to distort the negative cloud much more. And secondly, charge on the ion, greater the charge, it is better. So, that is regarding the polarizing power of ions there. And essentially, if you really ask me, the better indicator is the charge density, because there are two parts of it. One, the charge, second is the size. So, charge density is a better indicator. Let us take an example here. Look at this, I got three ions here, lithium ion, sodium ion and potassium ion there. all the three of them have got 1 unit of charge each. So, in terms of charge they are equal there. And if you look at the charge density will be in this order. Lithium will be having more charge density than the sodium, which will be more than the potassium ion there. The reason being the charge is the same, but the denominator is different over there. So, the size is much smaller here, so charge density will be much larger over here. And we find that the polarizing power also varies in the same direction there. Lithium ion is more polarizing than sodium ion, which is more polarizing than the potassium ion there. Let us take another example. Now, suppose I take 3 different ions. This is sodium ion, magnesium ion, aluminum ion. So, what you find is the charges are different now. This is 1 unit charge, this is 2 units of charge, this is 3 units of charge. And also what we see is the sizes are different. And if we try to work out the charge density, it will be largest here in case of aluminum. The charge is maximum, size is the minimum over here. So, this density is the maximum over there. So, that is the order of charge density, and same is true of the order of polarizing power over there. So, essentially when we talk about the polarizing power, how powerful is a given ion to polarize the other ion, that will depend on the charge density, that is the charge to size ratio of that particular ion there. Let us move further and look at a second factor there. Second factor is polarizability of the ion. So, the issue goes like this, that we have got 2 ions, say one positive ion here, one negative ion here. This positive ion is trying to polarize this negative ion over there. So, what is the polarizing power of this? That is one factor. Secondly is how easy is for this molecule or this particular ion to get polarized. So, the 2 factors are going to contribute to the covalency in ionic compounds over there. So, the polarizability of the ions is basically the ability of an ion to get polarized there. Essentially, it is a tendency of the ions to get distorted or kind of polarized there. And this depends on the diffusedness of the electron cloud, that is how diffused is the electron cloud there. We know that as the ion becomes larger and larger, the electrons are get slightly they get away from the nucleus and they are slightly loosely held. So, they get easily polarizable. So, the polarizability of a negative ion is greater than that of a positive ion, because the electrons in them are less firm, because in the case of a positive ion the electrons are less firmly bound there. And large negative ions are more polarizable than the small ones, which we just saw earlier also. So, what we see here is that we have seen so far that by putting our arguments here, we find that the ionic compounds are not pure ionic compounds, there is certain element of covalency, and that covalency depends on 2 main factors there. One, the polarizing power of cations or the ions there, and the polarizability of the ions, the 2 factors. So, these things which determine or which kind of bring in the concept of covalency. So, all these factors have been put together by Fajan in terms of certain rules there, they called as Fajan's rules. They basically outline the factors that favor polarization of ions, which in turn introduce covalency in the ionic solids over there. And these rules happen to be following the 4 factors which have been put forth by Fajan, and they happen to be small cation, large anion, large charge on one or both the ions, and non-noble gas configuration of the cation. These factors we already have discussed here. Small cation will be having more polarizing power, large anion will be more polarizable, large charge on any of the 2 ions is going to make it more polarizing power over there. And if we have got a cation having a non-noble gas configuration, it will be easily polarizable over there. Okay, so that is as regards the concept of covalency and the Fajan's rules which outline the factors for them. Let us move further and talk about the process of dissolution. Now, we know that a solution is a homogeneous mixture of 2 or more substances. This is something very trivial which we all know fairly well. Just for sake of completeness of argument, I am trying to put it here. And we also know that in a solution the component in the largest amount is called as a solvent and other components are called as solute. There are different types of solutions depending on the physical state of the solute and the solvent, and we will be talking about systems wherein we have got one solid solute and solvent is a liquid there. That is, we will be talking about solutions of 2 components only. The larger component will be solvent, smaller will be solute there. Now, let us see what is this process of dissolution. We all know that suppose I take a glass of water and take a spoonful of sugar or salt, put into this and stir it, it dissolves. So, that is dissolution. Now, but what is happening at the molecular level? At the molecular level, what happens is the solute particles. So, the example I have taken sodium chloride or sugar particles there. So, they are the one which disperse throughout a solvent water in this particular example over here. In this process, what happens is the solute particles, say sodium chloride, the sodium ion and chloride ions, they will disperse into solvent and occupy the positions which were already occupied by the solvents there. Solvents will move out and solute will come in over there. So, this process what we get is, we get a solution there, and the ease of this process depends on the relative strengths of the following things over there: solvent-solvent interactions, solute-solute interactions and solvent-solute interaction. That means the whole process of dissolution is based on these three sets of interactions there. We got, say, sugar, you got water. So, in case of sugar, there is a sugar-sugar interaction there. In water molecules, you got water-water interaction. When you mix the two together, a new interaction comes into play, that is between sugar and water interaction. So, the whole process of dissolution is an interplay of these three sets of interactions there. So, depending on the strength of the mutual strengths of these things, we try to work out whether the things will dissolve or not dissolve there. We will come to that when we talk in the terms of the energetics of this process. Okay. Now, let us recall that when we talk about intermolecular interactions, what are different possibilities there? You remember that we talked about induced dipole interactions, which come into play when we talk about non-polar molecules there. We also talked about induced dipole interactions, and then we did talk about ion induced dipole. This is very pertinent when we talk about dissolution process there, dipole-dipole interaction, and then we did talk about ion dipole. This is very pertinent when we talk about dissolution in water there, because water is a dipole and ionic solid in water is, this is a very predominant kind of interaction over there. Then we also have got hydrogen bonding, which is typically a very important interaction, because the water is highly hydrogen bonded. So, that is a starting point for water. With these interactions have to be broken for solution to be formed there. Okay, let us continue and try to visualize the process of dissolution. Let me say, so I take the same example again. I have got sugar, I am trying to dissolve it into water. So, what is the first step there? We can think of the first step to be separation of the solvent molecules. In this step, what happens is, we have got solvent particles which are bonded to each other by whatever kind of interactions, depending on what solvent I am talking about. And these particles of solvent, they separate out, and some amount of energy is required for this process. That is step number 1 in the dissolution. Step number 2 is separation of solute particles, say sugar molecules. Sugar molecules are compactly packed in the crystal there, they separate out. This again involves certain amount of energy there. And the third step happens to be the mixing of these two. That means, we have got, say, water molecules which have got separated out, we have got sugar molecules which are separated out, then the two mix together to give me a solution here. So, this is a representation of a sugar solution in water for that matter. So, that is the way we can visualize the process of dissolution: solvent particles getting separated, then solute getting separated, the two separate set of particles getting mixed with one another. So, that is the process we are talking about. Now, and in this process, the following set of intermolecular interactions have to come in play. One is solvent-solute interaction, or we got solvent-solvent interaction and solute-solute interaction. This becomes operative when the solvent particles have to separate out. So, this interaction has to be broken. Similarly, in the second step we talked about, the solute-solute interaction had to be broken there. And in the third step, when we talk about mixing, this solvent and solute interaction come into picture there. So, what is the relative magnitude of this set of interactions, that is going to determine whether the things are going to be dissolved or not, if yes, to what extent. So, all that is taken care of in terms of these three sets of interactions there. Okay. Now, let us try to see what is the energetics of this process of dissolution. The energetics of process of dissolution can be seen in terms of energies of the associated processes, because we got three steps over there. So, what is the energy of each step of them? Separation of solid particles is called as delta H solute, is the energy involved in the process. Separation of solvent particles, you got delta H solvent there. Mixing of solute and solvent particles, it is delta H mixing there. And what you find is the overall enthalpy change, that means when the solution is formed, the total energy change happens to be delta H solution here, and this delta H solution will be equal to the sum of these three terms over there, because this energy is required, this energy is required, this energy is released. So, sum of these three is going to give me the total energy of the whole process as a whole. We know that according to Hess's law, we can write down the delta H solution to be equal to sum of these terms over there, and what you see is that the first term here, delta H solute, that is the energy required for solute particle to separate out, is always greater than 0, because we do need energy to separate them, because the solute particles are holding each other, some kind of interaction is there, that interaction has to be broken for them to be separated out. Similarly, delta H solvent also is greater than 0, because here again we need energy to separate out the solvent particles from each other. In the third step here, delta H mixing is always less than 0, because when the two mix together, certain amount of energy is released in the process. Now, the sign of delta H solution, that is the overall process, will depend on some of these three terms there. And if we add the three terms, depending on what is the relative magnitudes of delta H mixing as compared to the sum of these two, that is going to determine whether it is going to be negative or positive. Let us look at this. Now, let us look at the energy changes during dissolution process in terms of a diagrammatic representation. We will do it for the exothermic dissolution first. That means a process of dissolution which is accompanied by release of energy. Let us see how does it happen. We start with, say, solvent particles there, they separate out, and this is the energy change delta H solvent over there. Similarly, we start with the solute, that also separates out, and this is the energy involved in that, delta H solute. Both these energies are required to be supplied from outside, and the total energy supplied is sum of these two. That means this is for the solvent, this is for the solute put together. So, initially this was my energy, now the energy becomes so much here. But what happens in the third step is these two, the solvent particles are separated out and the solute particles which are separated out, the two mix together and give rise to a solution here. And the energy in this process is so much of energy is released in this process. This is my delta H mixing there. Now, if this be so, then what you find is I started with this amount of energy, I supplied so much energy, energy became so much, and now the energy released is larger than the energy total supplied to earlier. So, that means in nutshell we can say that there is a net energy released in the process, and this is the energy which is released in the process. This is called as delta H solution there. And a typical example for this is magnesium sulfate in water. If you take magnesium sulfate, dissolve in water, we find that the solution becomes slightly warm there, because energy is released in the process. Now, let us take the second case now. We are talking about now a process which is endothermic dissolution. That means a dissolution process which is associated with the absorption of energy there. Let us look at it. That means we start again solvent sample there which separates out. So, this is delta H solvent there. Similarly, what we had earlier, we have the solute particles which are separating out, delta H solute is there, total amount of energy supplied is so much, sum of these two energies there, and when the two mix together, what I get is a solution here. In this case, what I find, the energy released in the process of mixing is just this much. This is my delta H mixing here. So, what I find is, I started with this amount of energy, I supplied so much, but what I got energy back is less than that. That means essentially it amounts to that I have absorbed certain amount of energy. That means this process of dissolution is associated with absorption of energy, and this energy which has been absorbed is my delta H solution there. And typical example for such a process is ammonium nitrate in water. You take ammonium nitrate, dissolve in water, the solution becomes slightly cool, and these are got applications in different domains there. Now, let us see what happens, what is the possibility of these processes to take place there. If a dissolution process is an exothermic process, it will tend to proceed spontaneously. That means a process will occur on its own. But if it happens to be endothermic, it may so happen, if it is slightly endothermic process, it will be proceeding because of the entropic reasons involved there. Because when this process of mixing takes place between the separated solvent particles and separate solute particles, the entropy of the system increases enormously. Even if there is a small enthalpy change required, that is taken care of by the enthalpy changes there. So, this is a kind of an enthalpy driven reaction there. But if the process happens to be highly endothermic, in that case it may not occur at all. And so, when we try to talk about dissolution, essentially we have to think of the solvent in such a fashion that delta H mixing, that is the energy released in the process of mixing, should be either equal to the sum of the energies required for the two processes or greater than that. The greater than that will be making it exothermic, and almost equal to that will make it roughly exothermic, and that is possible to proceed because of the entropy regions there. Let us go further and come down to dissolution of ionic solids per se, because we talked about dissolution and the energetics of that process. If the ionic solid is there, then what do we do in that case? The ionic solids also dissolve in the same fashion. That is, we got these three steps there: separation of solid particles, solvent particles, and mixing the two together. But in this case, what we do is, the step 2 and 3, they are actually combined together into one, and the energy involved in this process is called as the solvation energy. That means the solid particles are separated out, and because basically you got an ionic solid. When you say the solid particles separated out, essentially we have broken that lattice, we have supplied the lattice energy to that, and all ions are there in the gaseous phase. Now these ions in the gaseous phase then react with the solvent particles there, and this process, the solvent particles solvate the ions there. That means there is an ion dipole interaction kind of a thing happen. So when that takes place, so this whole process is referred to as solvation, and if my solvent happens to be water, then this process is called as hydration. So the energy of step 2 and 3 put together is called as the hydration energy in case of water system, and solvation energy in general. Now the energy involved in step 1, as I mentioned earlier, for the separation of solid particle is the lattice energy, and the second, third step is the hydration energy there. Let us again look at this in terms of a diagrammatic representation. We have got an ionic solid now, an ionic solid that separates out to give me the corresponding ions over there, and the energy required for this process is delta H lattice. Essentially we have to break this lattice to get the ions over there. Then what happens is, these ions here which has broken down, they mix with the solvent here. I have taken water in this case. So this mixing takes place, and what happens is, the energy released in this process is called as a hydration energy, and what you get is, we get certain amount of water molecules are there, and there are these ions which were there, now they are hydrated over there, or solvated in general, hydrated in particular, because the water is a solvent over there. And in this process, this is the amount of energy which is required in this particular example over here. That means this process is associated with certain absorption of certain amount of energy there. If I look at the dissolution of ionic solids, we find that the enthalpy of solution would depend on relative magnitudes of the lattice energy and hydration energy, because there are two energies involved. One is the lattice energy, energy required to separate the solid particles there, and hydration energy, that essentially is energy released when the hydration of the ions takes place, or you get a solution over there. And there are three cases in this case. If delta H lattice happens to be equal to delta H hydration, we find that delta solution will be close to 0, and that are typical examples over there. If you take sodium chloride, put into water, that dissolves here, and what I get is delta H solution to be about 3.88 kilojoules. In case of sodium fluoride, it is almost 0.91. It is very small number there. These two processes do occur because of the entropic regions over there, but otherwise the delta H solution happens to be a small number there. That means whenever delta H lattice and hydration energy, they happen to be comparable, we get a very small delta H solution there. Look at the case 2. If delta H lattice happens to be much less than delta H hydration, our delta H solution will be greater than 0. It will be a process which will be exothermic, and all such dissolutions will be very quick, spontaneous, and it will be associated with the release of energy. And the examples here are lithium bromide or KOH put into water, what you get is there are solutions there, and there is corresponding energy involved in that. The third possibility is that if delta H lattice is more than the hydration energy, then what happens is delta H solution happens to be less than 0. It is an endothermic process. The typical examples I took it earlier also, that is ammonium nitrate. This makes the solution slightly cool there. Similarly, sodium nitrate also will make a slightly cool solution over there. Essentially what I am trying to convey here is that when you talk about dissolution of ionic solids in say water, so there are two things we have to compare: lattice energy, the energy required for the ionic solid to be broken up, and hydration energy, the energy obtained by solvation or hydration of these ions what are obtained in the first process there. So we compare the two energy, one energy is required, second energy is released. If the two are comparable, total value is close to 0. If lattice energy is more, I will need more energy there because it will be an endothermic process. If hydration energy is more, energy will be released there. So that is the whole play of the energies in case of dissolution of ionic solids over there. Okay, now I think that's all what we want to talk about dissolution process in general and also in case of ionic solids there. Let's sum up what we have done today. What we have done today is that we briefly reviewed the contents of the previous session, and thereafter we argued and established the covalency in case of ionic compounds. We took a lot of data for that purpose. Having done that, we moved on to the factors which affect the covalency in ionic solids, and in the process we explained Poisson's rules for the purpose. Thereafter, we talked about we described the process of dissolution as a matter of 3 steps over there, and then explained the energetics of this dissolution process. Having done that, we moved to a specific case of the dissolution of ionic solids. We described the process and explained the energetics in this process there. Now, with this, we come to the conclusion of this series of lectures on chemical bonding. Thank you.